Okay. Sorry, somehow I the recording seems to have stopped suddenly for some reason, and so I was unable to continue. Okay. So somehow that recording has stopped. So let me continue again. Uh, so we were here. So we were discussing in the part one of the lecture the probability, current, and density. Um, So the probability current and for density for the Dirac spanners is rho psi bar gamma 0 psi, and J bar is psi bar gamma is psi. Okay, because the bars we have defined now because in terms of daggers and gamma 0. With that, we can define del mu J mu is equal to 0. Now, if you look at the probability density, which is essentially rho psi bar gamma 0 psi, it is psi dagger gamma 0 psi, that is nothing but psi 1 square plus psi 2 square plus psi 3 square, which is not a Lorentz invariant quantity as expected actually, because we have seen that. So this is not really a Lorentz invariant quantity because it modifies under Lorentz transformations. Now, so let's go back to what we started off. We wanted to have what is the definition of whether these solutions, the momentum space solutions which we have derived earlier, whether they can represent physical particles or not. For that, they have to satisfy these two conditions, which are called the orthonormal conditions and the completeness relations. So this is what we are going to see. And now that we have defined what is bars, so we want to go back to the solutions first. Okay, so let's write down these four canonical solutions first for the Dirac equation. The four canonical solutions I represent now in terms of U and V. Okay, so the upper two components which I called, which I club the positive energy solutions, and the lower two components I club the negative energy solutions. We have seen that there are four solutions, right? Essentially, the positive energy up and down, spin up and down, and negative energy spin up and down. So let me write them down explicitly here. So the U, the first solution, is by some normalization factor given by the square root of E plus M, is represented in this particular fashion. So 1, 0, Pz by E plus M, 0, Pz by E plus M, Px plus Ipy by E plus M, and whole multiplied by E power minus the plane wave part essentially. Then we have the U2, which is the second solution, which is 0, 1. Instead of 1, 0, you have 0, 1. And Px minus Ipy will come by E plus M minus Pz, E power minus Px. Okay. So U1 and U2 solutions represent the particle solutions. Okay, U1 and U2 are the particle solutions of the equation, and the other two solutions are V1 and V2 for the antiparticles. So the particle solutions are U1 and U2, which are electrons, muons, top quark, all these particular set of solutions. And the antiparticle solutions are V1 and V2, which are positrons, antimuons, and so on. So the V1 is given with 0, 1, okay, for the case, and 1, 0 for the lower two components, not for the upper two components. So for example, 1, 0 for the upper two. So V1 is 0, 1 with a plane wave, which is essentially e power Ipx. So it's a negative energy solution, Px minus Ipy E by M minus Pz. N into N is nothing but the E power square root of E power E plus M. And V2, I think this has a minus sign here. This you can cross check it. Okay, is pz e plus m px plus ipy by e plus m 1 0. So v1 and v2 represent antiparticles. So this is v1 and v2 will represent, say, for example, positrons, antimuons, and antitops together. So, for example, so the wave function psi of the Dirac equation contains both psi. Say, for example, for the if you take it for the electron, the upper part contains the electron wave function, and the lower part contains the positron wave function. So just like we can define psi bar, we can also define psi bar for u bars and v bars also essentially. So when I say u and u here, they look like they are two component, but this is just a one way of representing them. But they're actually four component. U and v are separately four component. We can represent them as two component. Okay, I'm just grouping them like this. So I can define u bar as u dagger gamma 0 and v bar as v dagger gamma 0. These are four component solutions we have just seen. So the particles satisfy the momentum space equation p slash minus m u of 0. Okay. So these are all four component, by the way we are saying. Essentially, don't confuse them to be two component. The way, just because I have written it this way, two component spinors are different. Okay. So actually, I shouldn't write it this way. I should write it as u plus v. Okay. Psi is equal to, that's the correct way of writing it down. So, yeah, maybe not this also. This is also not correct actually. Yeah. Okay, so this is actually u plus v. Psi is no, there is no. This is correct. Okay, so u and v. Okay. So maybe I'll just, why confusing people? So I'll just write it down with a comma. Okay, then it's essentially same. So there are four solutions. I'm writing them one by one. Okay, where u are essentially electron wave functions and v are for positron, or say for example antitop, top, u is for top and v is for antitop, u is for proton, v is for antiproton. The u wave functions, the particle wave function satisfies this relation. So p slash minus m is equal to 0. Now you also want to define u bars, because you want to, just like you have psi bars, you also want to define, say, how the particle probability is going, say for example, okay, or how the particle current is going. So with this, you have p slash minus m u is equal to 0. This is the equation of motion, momentum space satisfied by particles. And u bar satisfies the relation p slash minus m is equal to 0. Now notice, remember that p slash minus m is a matrix and u is a column vector. This is equal to 0. And u bar is u dagger gamma 0, which is given in this particular fashion. So it picks up the minus sign for the other two. So it's a row vector which is multiplied. And so the u bar is u1 star, u2 star, minus u3 star, minus u4 star. Just check this. Where dagger is star transpose, right? Essentially. So this gives me this relation. So u bar satisfies this particular relations. Now for antiparticles, you have the other relations. So it is p slash plus m v is equal to 0. And v bar, this is for both 1 and 2, by the way. This is for both 1 and 2. Satisfies the relation. Again, p slash plus m is equal to 0. Except that, whereas the v satisfies the relation from on the right, the v bar satisfies the relation from the left. So these two, this will be given in the next assignment, need to be checked. and verified. Okay, I want all of you to check and verify. This will be need to be checked and verified. This will be some sort of an assignment I'll give you. Okay. Now with this, we can now check that. Okay, this is already there. I think there was some mistake earlier. So, but anyway, somehow the recording stopped in between, and I continued talking for about half an hour. And then anyway, so anyway, I had to re-record it again. So now let's look at this one. So orthonormal relations. So you have u bar 1 times u bar 2 is equal to 0. And v bar 1, v bar 2 is equal to 0. So u1 and u2 are orthogonal to each other. v1 and v2 bar are orthonormal to each other. And they are normalized. So you have u bar u is equal to m and v bar v is equal to minus 2m. These are the orthonormal relations. And the completeness relations are so the orthonormal relations are essentially the scalar parts. So if you want u bar u is a scalar. Okay, v bar v is also a scalar. So if you put the dagger here, so as we have seen that these are matrices, so these are column vectors. So this is what this is. So which is a scalar. So whereas the completeness relations are this times this, which is a matrix. So this is what we are going to get. So sum over alpha is equal to 1, 2, u bar alpha is equal to p slash plus m. Then similarly, alpha 1, 2, v bar alpha is equal to p slash minus m. You can re-express in terms of in a general fashion, essentially. So you get these continuous relation, completeness relations. So now, so today what we have started off trying to do is to derive these completeness relations and orthonormal relations to prove that the these the wave functions which we started off, okay, the wave functions which we started off to do, which are essentially meaning the Dirac solutions which we have seen, the 4 solutions which we have seen are not just complete. Okay, they're also orthonormal, so they can really represent the physical states. But to do that, we needed to introduce some. We had to see how the Dirac spinors transform under the Lorentz transformations, and that led to the introduction of the bars, the bar notation, because we had to define what a bar is, and we have seen that it doesn't really a dagger will not be sufficient to construct the Lorentz invariant and covariant quantities. We need to put the gamma 0 next to it. Okay, because the upper two components and the lower two components have a minus sign, and so they transform differently under the Lorentz transformations. So with this, we have introduced this gamma 0 and so the bar notation, and applying this bar, we can now define a Lorentz scalar like psi bar psi. So, and using this, okay, we can show not only this the continuity equation, but also show if you start with the momentum space solutions. With the momentum space solutions, we can define the completeness relations and representations of the particle that they are orthonormal, they're complete, and so we can have representations of physical particles can be represented in this particular fashion. Okay, so I'll stop here now, and maybe tomorrow I'll upload one more set of lectures. Okay, okay, thank you.